Welcome to the 8th lecture on properties of triangles. So, in this lecture also we will continue solving some difficult problems related to the properties of triangles that we have discussed in the previous lectures. So, here is the first problem. So, it is asking us to prove that r1 square plus r2 square plus r3 square plus r square is equal to 16 capital R square minus the sum of the squares of the sides of the triangles. So, minus a square minus b square minus c square, where the lowercase r is the in radius of the triangle ABC, the uppercase r is the circumradius, and r1, r2 and r3 are essentially the radius of the ascribed circles, the 3 ascribed circles of the triangle ABC. So, r1 is basically the radius of the ascribed circle which is opposite to angle A, and r2 is the radius of the ascribed circle opposite to angle B, and r3 is the radius of the ascribed circle opposite to angle C of the triangle ABC. So, how do we go about solving this problem? What we see on the right hand side is we see the square of the circumradius, and then we see the squares of the sides of the triangle. So, this reminds us of one identity that we know, which is that the circumradius r is equal to a upon 2 sine A is equal to b upon 2 sine B is equal to c upon 2 sine C. So, from here what we get is that A is equal to 2 r sine A, B is equal to 2 r sine B, and C is equal to 2 r sine C. So, if we replace these expressions for A, B and C on the right hand side, then essentially we can take r square out as common. So, what this is going to become equal to is that, so the right hand side is going to be equal to 16 r square minus 4 r square sine square A minus 4 r square sine square B minus 4 r square sine square C. So, we see that we have r square in each one of the terms here, and so essentially this entire thing will be equal to 4 r square times 4 minus sine square A minus sine square B minus sine square C. So, now that we have the square of the circumradius on the right hand side, we should do something to have the square of the circumradius on the left hand side also. So, if we go in that direction, then we already know that the in radius of the triangle ABC is equal to 4 times the circumradius times the product of the sine of the half angles of the triangle. So, this identity is known to us. So, essentially if we use this expression here, then we will get 16 r square times sine square A by 2 sine square B by 2 and times sine square C by 2. So, we will get r square like that. So, we hope to then therefore replace r1, r2 and r3 also by similar kind of an expression, which is basically the product of the circumradius times sine or cosine of some of the angles of the triangle ABC. So, if we recollect, then in one of the previous lectures where we were discussing the ascribed circles of the triangle ABC, we had shown that the radius of the ascribed circle opposite to angle A is equal to the area of the triangle ABC divided by S minus A. Similarly, R2 is area divided by S minus B, and R3 is area divided by S minus C. But then we know that from the Hero's formula, we know that the area is simply the square root of S times S minus A times S minus B times S minus C. So, if we replace the area here by this expression, what we get is that R1 is equal to square root of S into S minus B into S minus C upon, so there is a divide by S minus A. So, we will get a S minus A in the denominator in the square root, and this can also be then written as S times square root of S minus B into S minus C upon S into S minus A. Again, from the previous lectures, we know that sine of the half angle of A is equal to square root of S minus B into S minus C over B C, and the cosine of half angle A is equal to square root of S into S minus A over B C. And therefore, if by looking at these two expressions, it is not very difficult to see that this expression here is nothing but sin A by 2 divided by cos A by 2, and therefore, this is sin A by 2 divided by cos A by 2 is tangent of A by 2. So, therefore, another formula for R1 is S times tan A by 2. Taking this to the next slide. So, we have so far shown that R1 is S tan A by 2. We also know that the in radius is given by the area of the triangle divided by the semi perimeter S, and therefore, from here we have that the semi perimeter S is equal to the area divided by the in radius. So, if we replace this S by delta upon R, what we get is R1 is equal to delta upon R into tan A by 2. But remember, we have to get this to be equal to the circumradius times something. So, this is our, and the reason why we want it to be like that is because we already know that we got the right hand side to be r square times something, and we already saw that the square of the in radius can be written as 16r square times the product of the squares of the sine of the half angles. So, we expect to also have an r square in each of these three terms here, so that we can then cancel r square from both the sides, and what we will be left with is only trigonometric functions. Further, we also know that the circumradius of the triangle ABC is equal to the product of the sides divided by 4 times the area of the triangle, or alternatively this also means that the area is equal to ABC by 4r. So, if we replace this delta by ABC by 4r, what we get is R1 is ABC by 4r uppercase R into tan A by 2 And then as written on the previous slide, we also have this expression that the in radius is 4r times sine a by 2 sine b by 2 sine c by 2. So, if we use this over here, what we get is that r1 equals abc by 16r square. So, we have tan a by 2 in the numerator, in the denominator we get this product. So, now we do have r on the right hand side here, but then we wanted the r to be in the numerator, right. So, and these are all trigonometric functions. So, we need to do something with this a, b and c. Can we express each one of them as r times something, as a product. So, we need to write all of this a, b and c as the product of the circumradius into some trigonometric function. So, that reminds us immediately of the fact that what we saw on the just previous slide, which is here, which is that a, b and c are nothing but twice the circumradius times the sine of the corresponding angle. So, when we use these three instead of a, b, c in this equation here, what we get is 8r cube times sine a, sine b, sine c into tan a by 2 divided by 16r square times sine a by 2 sine b by 2 into sine c by 2. So, upon simplification, that gives us r1 equals. So, now we get r in the numerator, and that only happened because we got r cube here after we replaced all of these a, b and c by the product of the circumradius times the 2 times the sine of the corresponding angle. So, rewriting the expressions from the previous slide. And then of course, we use the formula that sine of a is nothing but 2 times sine a by 2 times cos a by 2. So, we will use this fact, sine a equals and similarly for sine b and sine c. So, what we will ultimately end up getting is r1 equal to 4 r times. So, this is going to give us 2. So, sine a by 2 will get cancelled, we get cos a by 2, but that will get multiplied with tan a by 2. So, we get sine a by 2 here, and then cos, because when we write sine b in this form, then sine b by 2 will get cancelled, and what remains is only cos b by 2 in the numerator and cos c by 2 from these two. So, these two give cos c by 2, these two gives us cos b by 2, and then the remaining gives us sin a by 2. So, this is what is the intermediate result that is going to help us to prove the equality between the left hand side and the right hand side in this problem. So, we are going to replace this expression, we are going to replace r1 in this equation by this expression. So, basically what we are going to do now is we are going to replace all of these r1, r2 and r3 by their corresponding expressions of this form, and then sum all of them up and do some with some simplification we should be able to get this right hand side. So, just like we did it for R1, we can also show that R2 is equal to 4R times sin B by 2 into cos A by 2 into cos C by 2, and R3 is equal to 4R times sin C by 2 into cos A by 2 into cos B by 2. So, let us now use these expressions on the left hand side, and of course, we also have R equal to 4R into sin A by 2 into sin B by 2 into sin C by 2. So, then the left hand side, which is R1 square plus R2 square plus R3 square plus R square equals, so 16R square is going to be common because all of these have 4R, and that is what we wanted. So, this is going to be equal to plus R3 square. So, R3 square is plus R square, which is so we have to show that this is equal to, this left hand side is equal to the RHS, which is 4R square into 4 minus so this is what we have to show. So, this is the RHS. So, going back to the left hand side expression, so the LHS is equal to 16R square into, so we will take sine square, if you see sine square A by 2 is here and it is also there in the last term. So, we will combine those two terms which have sine square A by 2 as common, and then so this term plus this term gives us and then when we add the, so the remaining two terms have cos square A by 2 as common. So, we have into cos square B by 2. So, we will try to move this 16 inside because we have cos square of an angle, and so if you recollect, then 2 cos square theta is equal to 1 plus cos 2 theta, and 2 sin square theta is 1 minus cos 2 theta. We will use these two results here now. So, since we need a factor of 2, so we will have to move, we need a factor of 2 for this and 2 for this. So, we will have to move 4 inside. So, what remains here is 4r square sine square a by 2 times plus 2 sine square b by 2 times 2 sine square c by 2, and similarly for the other term also, which will be 4r square cos square a by 2 into 2 sine square b by 2 into 2 cos square c by 2 plus 2 sine square c by 2 times 2 cos square b by 2. And then for each of these 2 cos square or 2 sine square, we are going to use these identities. So, the left hand side then becomes equal to 4r square sine square a by 2 times. So, this term here is equal to 1 plus cos of b, this is 1 plus cos c. Similarly, this is 1 minus cos b and 1 minus cos c. So, this is what we get. By replacing all of these terms to be of the form either 1 plus cos theta or 1 minus cos theta, and then simple multiplication gives us so this term inside this square bracket will get simplified to 2 plus 2 cos b cos c. Similarly, this other term will get simplified to that can be further written as, so we have 8r square. So, this multiplied by this is 8r square sine square a by 2, and then here we get 8r square cos square a by 2, but we know that sine square a by 2 plus cos square a by 2 is 1, and therefore, we will simply have 8r square plus, and then this multiplied by this and this multiplied by this. So, what we will get then is 8r square into sine square a by 2 into cos b cos c minus 8r square cos square a by 2 into cos b cos c. But here we see that essentially, because this 8r square and cos b cos c is common, what we see here is cos square a by 2 minus sin square a by 2 coming here. So then the left hand side is equal to 8r square plus 8r square cos b cos c times sin square a by 2 minus cos square a by 2, which is equal to 8r square minus 8r square into cos a cos b cos c, because this is equal to minus of cos a. So here we have for this we have used this formula that cos 2 theta is cos square theta minus sin square theta, with theta equal to a by 2. And this can be further written as 8r square into, so cos c, because a plus b plus c is pi, c is equal to pi minus a plus b, and therefore cos of c is cos of pi minus a plus b, which is minus cos a plus b. So here we have used the result that cos of pi minus theta is equal to minus cos theta for any theta. So using this result here, what we have is, if we replace this cos c with this, what we get is a plus sign here and cos of a plus b there. But then we have this cos a cos b, so we'll try to use the 2 cos a cos b formula. So we'll make this 4 and we'll bring a 2 here, and we know that 2 cos a cos b is cos a plus b plus cos a minus b, and then times cos a plus b, which is equal to 8r square plus 4r square into cos square a plus b plus cos a minus b into cos a plus b. But cos square a plus b is the same as cos square c. So we will replace this with cos square c. Plus now cos of a minus b into cos of a plus b is equal to half times which is equal, and this thing is equal to, of course, cos of this plus this, which is 2a, plus cos of this minus this, which is 2b. cos 2a is 2 cos square a minus 1 plus cos 2b can be written as 1 minus 2 sin square b. So, reason why I wrote in terms of sin b is because I wanted this minus 1 and plus 1 to get cancelled. So, that is why I chose this form for cos 2b and this form for cos 2a. So, this becomes equal to cos square a minus sin square b. And then of course, we will use this expression over here, and then we get the left hand side to be equal to 8 r square plus 4 r square into cos square c plus cos square a minus sin square b. So, what we have done is that in the previous slide, instead of cos a minus b into cos a plus b, we have replaced it with this expression. And that is equal to so we can write this as 1 minus sin square c and this as 1 minus sin square a, and then of course we have minus sin square b, because if we remember on the right hand side here we have the squares of all the signs, and therefore, to prove this left hand side to be equal to the right hand side, we have to convert all of these cosine to sine, and then 1 plus 1 is 2 and 2 times 4 r square is 8 r square. So, we get 16 r square here minus 4 r square into and this is exactly what is the right hand side that we wanted to show. 16 r square, we have 16 r square here minus 4 r square into the sum of the squares of the signs. So, minus and then 4 r square. So, that finishes the solution to the first problem. So, this is the second problem. Here we are asked to prove that in any triangle ABC, the distance between the circumcenter and the orthocenter is given by this expression, and then further that the distance between the circumcenter and the centroid is given by this expression. So, let us first prove the first part, and then we will show that the second part will follow pretty much easily. So, to solve this problem, let us first draw this triangle ABC. So, let this be the triangle ABC. The point of intersection of the two perpendiculars is the orthocenter P. So, P is the orthocenter, and then the circumcenter is simply the intersection of the perpendicular bisectors of the sides. So, this point O is the circumcenter. and the problem is asking us to find an expression for the length of this line segment OP, which is the distance between the circumcenter and the orthocenter. So, towards solving this problem, let us first connect O with A, and we will also connect O with B. Of course, since O is a circumcenter, we know that OA is equal to OB is equal to the circumradius R, and then since we have to find OP, we see that OP is a side of this triangle OAP, and we already know the length of OA. If we apply the cosine formula to this angle OAP, we have cos of angle OAP equals OA square plus AP square minus OP square upon 2 times OA times AP. So, from here we can derive an expression of OP square as OP square is equal to OA square plus AP square minus 2 times OA times AP times cos of angle OAP. We already know that OA is R, OA is equal to R. Therefore, if we can somehow find an expression for AP and the value of this angle OAP, then by substituting those expressions we should be able to get an expression for OP. So, that is the approach we are going to take. Let us find an expression for this length AP. Now, we know that the length of this side is C, and because let us say this point is D, because DBA is a right angle triangle with C as the hypotenuse, this length is C cos A. Further, this angle is pi by 2 minus C, because if we look at this right angle triangle, this angle is C, and therefore, this angle has to be pi by 2 minus C. Next, if we look at the triangle APD, which is also a right angle triangle, we see that AP is equal to AD, which is C cos A, divided by cosine of this angle, which is sine of C, because cosine of pi by 2 minus C is sine of C. But we already know that the circumradius is equal to C upon 2 sin C, and therefore, C upon sin C is 2 times the circumradius, and hence this expression is equal to 2 times the circumradius times cosine of A. Now, what remains to find is just the angle OAP. We know that this is already pi by 2 minus C. Because O is the circumcenter, we are basically going to have a circumcircle like this, which is going to touch all the 3 vertices, something like this. And therefore, from our basic high school, we know that if we have a circle like this, and let us say this point is A, this is B, and this is C here. So, this is our triangle ABC. I have just turned it a little bit. Then from high school algebra, we know that this angle is twice of this angle, and therefore, this angle is 2 times C. But since this green line is the perpendicular bisector of this side, this is 90, this is 90, and therefore, this angle will be half of 2c, which is c, and because this triangle is a right angle triangle, this angle here will be pi by 2 minus c. So, this angle is pi by 2 minus c, this is pi by 2 minus c, this entire angle is a. So, now we should be able to find angle OAP equal to a minus 2 times pi by 2 minus c, because we have pi by 2 minus c 2 times. And this is equal to a plus 2c minus pi, but pi is equal to a plus b plus c, and therefore, if we put a plus b plus c here instead, we will get this angle to be equal to c minus b. So, now if we use this equation with these values of AP and the angle OAP, we get OP square equal to, so OA square is r square plus 4r square cos square A minus 2 times OA, which is r, times AP, which is 2r cos A, times cosine of angle OAP, which is cosine of c minus b. And then this is equal to r square plus 4r square cos A into cos A minus cos of c minus b. But we know that because A is equal to pi minus b plus c, cosine of A is minus of cosine of b plus c. So, we use this fact here, we have OP square as r square plus 4r square into cosine of A minus cosine b plus c minus cosine c minus b. And then we can use the cos x plus cos y type formula. We will get, so we will take this minus outside. This will become 2 times cos b into cos c, and therefore, we get finally OP square as therefore, OP is equal to, take the square root, which is essentially what was asked to prove. But this only finishes the first part. We are also asked to find the distance between the circumcenter and the centroid. So, that might seem tough, but it is not very difficult, because in one of the previous lectures we had seen that, and we had in fact proven it, that if this is the circumcenter and this is the orthocenter, let this be the line segment joining the circumcenter to the orthocenter, then we had shown that the centroid will also lie on this line. So, the centroid G will lie on this line, and it will divide this line segment in the ratio 2:1. So, it will be closer to the circumcenter. And therefore, from here it is easy to see that OG is equal to OP upon 3, and we have already derived an expression for OP just now. So, we just need to divide this by 3, and then of course, some manipulations have to be done. So, after we do that, it is not very difficult to get this expression for the distance between the circumcenter and the centroid, which is this distance. So, that finishes the solution to the second problem. Let us take the third problem now. So, here we are asked to prove that in a triangle ABC, the triangle is equilateral if and only if this condition holds. Of course, if triangle ABC is equilateral, then we have A equal to B equal to C equal to pi by 3, 60 degrees. And then if we replace these values on the left hand side, then we get three times root 3, because each one of them is root 3. We know that tan of pi by 3 is square root of 3. So, using this result we have this. So, this part is okay, that if it is equilateral, then it is very easy to show that this condition is getting satisfied. But because we are asked to show if and only if, we have to also prove the converse. So, the converse is that if we have a triangle ABC, and if it so holds that this equation is true, then we have to prove that A, B and C are all equal to 60 degree. So, that is what we are going to do next. So, suppose we have a triangle ABC where the angles A, B, and C are such that tan A plus tan B plus tan C is 3 times square root of 3. We will now show that this will imply that A, B and C are all equal. In any triangle, A plus B is pi minus C, and therefore, tan of A plus B is tan of pi minus C, which is minus tan C. But here we use the tan A plus B formula. So, tan A plus B is tan A plus tan B divided by 1 minus tan A tan B. Therefore, if this is true, then tan A plus tan B upon 1 minus tan A tan B equals minus tan C, and simplifying this will give us tan A plus tan B plus tan C equals tan A into tan B into tan C. But we already started with this condition to be true, and since now we have shown that in any triangle this is equal to this. So, this part is very general. This entity is true for any triangle. In the problem, it is stated that the angles A, B and C further satisfy this equality. So, since this is equal to the product of the tans of the angle, it is obvious that in this problem the product of the tan of the angle should also be equal to 3 times square root of. So, now this expression is the product of 3 real numbers. The product of 3 real numbers is positive, which implies that either all of them are positive or exactly 2 are negative and the third one is positive. But if exactly 2 of them are negative, it basically means that because we know that from the graph of the tan function, if we recollect the graph of the tan function. So, let us say this is pi by 2 and this is pi, this is 0. So, it used to be something like this. So, there used to be a discontinuity at x equal to pi by 2 and then and of course, this repeats because the tan function is periodic with pi. Since these angles A and B and C have to be between 0 and pi, for tan of any of these angles to be negative, the angle must be greater than pi by 2. So, that is clear from this graph. But in a triangle ABC, in any triangle, 2 angles cannot be more than pi by 2, that is not possible. And since 2 angles cannot be more than pi by 2, it is clear that for the 3 of these terms, we cannot have a situation where exactly 2 of them are negative. So, that is not a possibility, and therefore, the only possibility that remains is that all 3 of them are positive, or basically all of these are positive, which basically implies that all the angles A, B and C are between 0 and 90 degrees, or basically this triangle is an acute triangle. And further, here if we see this equation, so we have now shown that tan A, tan B and tan C are all positive, real valued. Now, from the arithmetic geometric mean inequality, so we know that AM is greater than equal to GM. So, let us consider these 3 numbers. So, the 3 numbers are tan A, tan B and tan C. So, their arithmetic mean is this, and this has to be greater than equal to the geometric mean. So, the geometric mean is tan A into tan B into tan C to the power of, so the third root of their product. Now, in this case, we already know that the product of the tans, the product of the tan of the angle and the sum of the tan of the angles are both equal to 3 times square root of 3. So, let us try to evaluate the left hand side for the problem that we have been given. So, the left hand side will come out to be 3 root 3 divided by 3, which is square root of 3. That is because we initially started with this equation. The right hand side, which is this, will be equal to, since in any triangle we have already shown this equality, it is clear that the product of the tans is 3 root 3 for this particular problem, and therefore, the right hand side will be the cubic root of 3 root 3, which is equal to, so this 3 we can write as root 3 multiplied by root 3. So, that is this 3 multiplied by this root 3 to the power 1 by 3, which of course is equal to root 3. So, what we see is that for this problem, the left hand side and the right hand side of the AM-GM inequality are equal. And we know that in the AM-GM inequality, if the left hand side and the right hand side are equal, what it implies is that all of the real numbers have to be equal to each other. So, if we so essentially we know that if we have three positive numbers x, y and z, then this is always true. But if suppose we somehow show that this is exactly equal to this, then that will imply that x equal to y equal to z. So, this is the result that we are using here with x equal to tan A, y equal to tan B and z equal to tan C. Since we are getting equality in this AMGM inequality, because we showed that this left hand side is root 3 and the right hand side is also root 3, and therefore, it is implied that all these three are equal to each other, that is tan A is equal to tan B is equal to tan C. And since all these angles are acute angles, if we go back to our graph here, all of these angles A, B and C have to lie between 0 and pi by 2, and in this interval tan x function is monotonically increasing, and therefore, if the tan of three angles are equal, the only possibility is that these three angles are equal to each other, and hence it is an equilateral triangle. So, that finishes the proof of the converse also, that if we start with this condition, then we have shown that this condition implies that the triangle is an equilateral triangle. So, that finishes the solution to the third problem. With this, we come to an end of this problem solving lecture. From the next lecture onwards, we will try to discuss a new topic, which is solution of triangles. Thank you.